Now, in this question it says a 10 milligram effervescent tablet containing sodium bicarbonate and oxalic acid release 0.25 ml of CO2 at temperature 298.15 Kelvin and pressure is equal to 1 bar. If molar volume of CO2 is 25 liter under such condition, what is the percentage of sodium bicarbonate in each tablet? It is also given that the molecular mass of NaHCO3 is 84. So first of all, let us write the balance reaction. Sodium bicarbonate is going to react with oxalic acid to give us CO2. This is sodium oxalate plus H2. This is a balance reaction. So we can see that if 2 moles of NaCO3 reacts, it produces 2 moles of CO2. So from the stoichiometry of the equation, moles of CO2 produced is equal to moles of NaHCO3 which is reacted. So what is the moles of CO2 produced? We can use, because volume is given, we can use N is equal to PV upon RT. Pressure is 1. Volume is 0.25 ml. So therefore converting to liter upon 0.0821 into 298.515. This is the number of moles of CO2 produced. From the stoichiometry we can say that the moles of NaHCO3 therefore will also be same. And weight of NaHCO3, we can multiply this with the molecular weight. We are further multiplying by 10 raised to power minus 3 because we want the weight in milligram, because the sample weight is given as 10 milligram. That comes out to be 0.856. So in terms of percentage, it is 8.56. So we can see for this question, answer comes out to be A. Next. In this question it says 2 closed bulbs of equal volume V containing an ideal gas initially at pressure Pi and temperature T1 are connected through a narrow tube of negligible volume as shown in the figure below. The temperature of one of the bulb is then raised to T2 and the final pressure Pf is. So this is the 2 bulbs connected by a tube of negligible volume. The initial pressures are Pi, V and T1. These are the pressure, volume and temperature conditions. Because we have not allowed the gas to escape, we can apply conservation of moles. So N1 plus N2, which are initial number of moles in A and B compartment, is equal to N1 dash plus N2 dash, which are the final one. What we are doing, the right hand side, we are increasing the temperature from T1 to T2. So applying conservation of mole, N is equal to PV upon RT. So initial Pi into V upon RT1 for the left one plus Pi into V upon RT1 for the right one. This is the initial condition. Final, the left side container remains at temperature T1. So it is Pf into V upon RT1 plus right side container is elevated to temperature T2. This is Pf into V upon RT2. We can see that the final pressure will be common because now the 2 chambers or bulbs are connected. So from here we can get the final pressure as this 2 Pi into T2 upon T1 plus T2. So we can see for this question answer comes out to be B. Next, in this question it says the given graph represents the variation of Z compressibility factor PV upon nRT PV versus P for the 3 real gases A, B and C. Identify the only incorrect statement. So if we talk about the real gas, we have the van der Waals gas equation for 1 mole P plus A by V square into V minus B is equal to RT, where A stands for intermolecular forces and B stands for volume occupied by the gas molecule. Now let us see option number A. It says for gas A is equal to 0. Its dependence on P is linear at all temperature. So we know that A gas cannot be liquefied because Z is more than 1. It is showing a positive deviation from the ideal gas. Therefore, intermolecular forces would be negligible in such cases, and therefore it is a correct statement and not the answer. For the second one, it says for gas B, B is equal to 0 and dependence on P is linear at all pressure. For gas B, we can see Z is less than 1. It is showing negative deviation from the ideal behavior at high pressures. Right? At high pressures, what happens is A becomes negligible and B is consistent. So we have 1 plus PB upon RT. Right? And it's so therefore, if B is 0, then at high pressure, Z will be equal to 1, which is not the case because we can see the slope is decreasing. So there is a contradiction in this statement. Right? And therefore, for this question, answer has to be B. Now D is correct because at high pressure the slope is positive for all real gases, because we know Z is equal to 1 plus Pb upon RT. And for C, which is a typical condition for a real gas, we can find by finding if we know the Z versus P, we can differentiate and find the critical pressure and all those things, and we can find the point of intersections. The minimum and the point of intersection with Z is equal to 1 and A is equal to B can be calculated. So that is very much the case, right? Therefore, the only incorrect option in this case is B.